Hello everyone. This is a continuation of the previous video uh, that I show you how to analyze the frame. And so after analyzing the frame, after finding all the known reaction at C and A and also internal reaction at B, we finally draw the corrected direction of the load or corrected direction of the reactions for each member, which is for member AB and member BC. So now once we get all this uh, internal reaction, we can draw the um, different diagram, which is your axial force diagram, shear force diagram, and BMD moment diagram. So in this case, for your axial force, we'll draw for the first for AFD, which is your axial force diagram. So for the member AB, we can say that for the axial force, we see that this value, what it does to a member AB, it apply as a compression. So we are going to draw that, and it's the same value, 5K and 5K. And so we'll note down negative means that the whole beam will experience a compression force of 5K. And then BC, there's no axial force, so we'll leave as it is, so it will become 0. So we'll just draw as it is. So this will be your axial force diagram. And then for the shear force diagram, so we'll draw again the same frame. We don't have to break the frame at B anymore, because this is the actual frame, and we're going to draw the diagram itself on the frame. And for the frame, we generally consider the local axis. What it means by that will mean that x, will consider x1, it is along the axis of the member, so that will be x1, and this will be y1. So this is called local axis, and this is called as global axis. So you can orient your axis, local axis, accordingly, but we know that generally anything along the axis of the member will consider that as your x-axis. So we'll assume that we'll consider this will be our local axis for the member AB. And so the 8K that we have here, the 8K we have here, it'll produce a positive shear. So positive shear, that means also for convenience, we follow exactly where the location, where the force is directing. So it's directing up, I mean to the left. So we'll also start from 0 and direct it to the left, 8K. And then because there is no external force in between A and the point load, so we have learned that if there's no force in between A and the point load 8K, it will be shear force will be slope equal to 0, which means that shear force will be straight line. And then exactly at the midpoint, you will have 8K coming down. So, and then after that, since again there's no load in between the point load 8K and joint B, so the shear force will be, again, slope will be 0, so it will be straight line. So, and the shear force will be equal to 0. So what it means, it means that this member, which means that this section of the member will experience a shear force of 8K, and this member will experience a shear force of 0. So there's no shear force at all in this half of the section, and half of the section will experience a positive shear force. And then for 5K, because this beam BC is the same as your global axis, so we'll draw 5K will go up in a positive shear, because this 5K will produce you a positive shear. And then because a beam member BC has a uniformly distributed load, and the load is downward, which is along the gravity. So your the concept here that we are that we have learned from the relationship between the shear force diagram and the load distribution is that if it is downward, so your slope will be negative. And because the UDL is because it's a uniformly distributed load, your slope will be 1. So which means that it has to be a straight line. And so we know that at this point C, it has to be slope downward. But we don't know what is the value around here at C. So what we have to do is we just cut this section, um, just cut the section at around C, and you'll see that that section, if you cut, and will follow the sign convention positive, so that will be your shear, and this will be 3 kips per feet, and that will be 12, sorry, that will be 4 feet. So if you use summation of all y equal to 0, you'll see v is equal to 12 kips. And so you'll see that v is equal to 12 kips, which is positive. So that means this point here will be 12 kips. So if you know that this is 12 kips and the force applied here is 25 kips, so the summation of all of those should also be 25. So if it is 12 kip upward, then downward should be 13 kips, such that the summation of all this summation will be equal to 25 kips. So now the slope has to go down till 25 or 12, 13 kips, and then there will be sudden reaction or sudden uh, vertical force because of the presence of the support C of a value equal to 25 kips, and then slope again will be negative, so it will go downward and then will be 0. So now we have positive shear, negative shear, and positive shear. So that will be your shear force diagram. And then for bending moment diagram, we'll draw again the same frame, and in this case you'll see that because we are drawing our local axis in this manner, your x1 and y1, so you'll see that what this moment will do to a beam, it will create a hogging. If it is hogging, that means it's a negative moment. So we are going to put here a negative moment of 40 kips feet, and because the shear force is slope 0, so that means for moment the shear force will be exactly slope equal to 1, which is your straight line, and this will be negative, which it means that it will be bent as a hogging. Okay, so you have that as negative. And then because moment is equal to 0 at B, so we know that it will be moment will be equal to 0. And because the shear force around here is equal to 0, so we know also that moment will be equal to 0. And here the shear force is not equal to 0, so that's why we also have moment not equal to 0. But because the slope is here is straight line which is equal to 0, so we have also the slope here which is equal to 1, which means that it should be linear. And here we found that the slope of the shear force is linear, and if it's linear, then the slope of the curve of the bending moment diagram will be 2, which means that it has to be a curve or a quadratic equation. So in this case, and what you will see here is this load, UDL load, will try to apply a hogging, a sagging. Okay, so this load in this region will be applying a sagging. So if you're applying a sagging, that means we know that the moment will be positive. And so if it is positive and around here, around C, so it'll be positive, it'll go, and how far it'll go, it reach maximum at where the distance is a, where the shear force is equal to 0. Here the shear force is equal to 0. That will be where you find the maximum moment. And then after that, we know that here at C, if you again cut the section, you know that this member, this section, because of this load, because of this UDL load, it apply a hogging. So we know that it'll have to be negative. So that means this will come down around here, and then it will go up. And if you wanted to know what is the moment around here, we can find that if we assume this as your M. So if you take summation of M equal to 0, you'll find M is equal to minus uh, 24 Gibbs feet. So you'll see that this is minus 24 Gibbs feet. So that will be your negative. And so this is how you draw the shear force diagram, axial force diagram, shear force diagram, and bending moment diagram in a frame. So the main thing is you must know the correct direction of your force. Okay, so once you have analyzed the frame, draw the members separately and with a corrected direction of your force. And then once you do that, then it'll be easy for you to follow and to draw the axial force diagram, shear force diagram, and bending moment diagram. Okay, and for if you wanted to know what is the A value here, like if you wanted to know what is the A value here, you have to use a similar triangle. And if you use similar triangle, you'll say that 5k, you can see that there's a triangle, small triangle, 5k divided by A, which is this small triangle here, will be equal to the big triangle over here. So the big triangle, it'll be equal to 5k plus 13k divided, and that length is 6 feet. So from here you can find what is A. And once you find A, which if A is around here, you can cut this section 5k. You can cut this section which is 3 kips per feet, and this distance is A. You can find what is moment, and whatever is moment equal to 0, and this will be your M max. You can find the value M max, which is kips feet, and you'll find that it is positive. Or what we have learned from the relationship between the bending moment diagram and the bending moment and shear force diagram, we can also calculate that the change in the moment from B to, let's say this is your D. So if you put this point around here, also D, or around here will be D, this point here D. What you can do is BD is equal to the area in your shear force diagram from BD, and this will be MD minus MB is equal to half base into height, or half height into base. Okay, and because this is positive, that's why we have, because this is a positive area, positive shear, so your area also will be positive. And we know that MB is equal to 0, so you can find that MD is equal to half 5 into A. So you can find also what is this MD, which is equivalent to M max is equal to half 5 into A. So once you find A value, you can either use this equation, cut the section at A, and then find what is your M max using equilibrium equation, or you can use the relationship between moment and shear force diagram by saying that the change in the bending moment from B to D is equal to the is equal to the integration or the area of the shear force diagram from B to D. And because change in moment from B to D will be MD minus MB, and MB we already know is equal to 0, moment at B is equal to 0, and this area from B to D is a triangle, so we know that will be half base into height, and from there you can find what is your maximum moment. So that's how you analyze the frame. You completely analyze the frame. First, you find the reaction, then you do the corrected direction of the force, and then after that, you draw all the required diagrams, which is your actual force diagram, shear force diagram, and bending moment diagram.